Hello, bachcho. Welcome to our first class on wave optics. Now, I know, some of you must be thinking, oh no, another difficult chapter. But trust me, we are going to make this so simple, so logical, that you will never forget it. I promise, we'll make sure every single concept is crystal clear, and most importantly, completely exam safe.
All right, let's start with something really simple. A question. I'm sure all of you have seen soap bubbles, I know. Those beautiful, swirling rainbow colors on them. But have you ever stopped and wondered, why? I mean, the soap water is just clear, right? So where are these colors coming from? Think about it. The rules you learned in ray optics, that light travels in straight lines, well, they just can't explain this beautiful mystery at all.
So what's the answer? Well, the answer, the one single key that unlocks this entire chapter and all its secrets, is this one simple idea. Light is a wave. That's it. Once you really get this, I'm telling you, everything else, interference, diffraction, polarization, it'll all just click into place. This is the big aha moment for this whole unit, bachcho. Okay, now look here. This is a very simple idea, but trust me, it's incredibly powerful. For a moment, just forget about light. Let's think about ripples in a pond. Simple, right? So, when the peak of one ripple, we call it a crest, meets the crest of another one, what do you think happens? Simple. They add up. They create a bigger wave. But what if a crest meets a trough, the lowest point of a wave? Well, they cancel each other out. Poof, gone. And believe it or not, it's exactly the same with light. So, two light waves meeting in step will give you brighter light, but two waves meeting out of step can create, believe it or not, complete darkness. Yes, you heard me right. Light plus light can equal darkness. All right, now for the official part, the formal NCERT definition. And I know, this equation looks a bit scary, doesn't it? But please don't worry about all the math here. For your exams, you just need to understand the meaning of two main parts. First, look at E naught, the amplitude. Just think of it as the maximum strength or brightness of the light wave. Simple. And the second one, this little symbol phi, is the phase. What's phase? It's just the starting point of the wave. Is it starting at the top, at the bottom, or somewhere in the middle? That's all it is. It's just about the timing of the wave. So let's see how this all fits together to build the most important concept in this entire chapter. Okay? Step 1. We now accept that light is a wave and it has something called phase. Good. Now imagine you have two waves. If their phase difference is constant, what does that mean? It means they are perfectly in sync, just like soldiers marching in step. We have a special name for this. We call them coherent waves. Now what if their phase difference is totally random, all over the place, like a chaotic crowd of people running around? Well, we call them incoherent. And this brings us to the most crucial point, the main takeaway from this slide. You will only see those stable, visible patterns of bright and dark spots if and only if the waves are coherent. And this table here, it shows you exactly what happens. It's brilliant. Just look at this simple example. Let's say you have two coherent light waves, and each has an intensity of I naught. If they meet perfectly in phase, 0 degrees difference, they do something called constructive interference. And look at the result. The new intensity is not 2 I naught, as you might expect. It's 4 I naught. Wow, 4 times the brightness. But now look at the other case. If they meet perfectly out of phase, 180 degrees apart, they interfere destructively. And the result? 0, complete and total darkness. This is the magic of coherent waves, you see. Okay, now everyone please pay very close attention. This is super important. These are what I call the silent killers in exams, the small mistakes where students unknowingly lose marks. First wrong idea, that two bright lights will always make an even brighter spot. This is only true for normal, everyday incoherent lights, like two tube lights in your room. But if the lights are coherent, like from a laser, they can actually interfere and create dark spots. Remember that. Second trap. Thinking that light always travels in perfectly straight lines. Ettery. We just learned that light is a wave, so it has to bend or diffract around edges. It always does. The only reason we don't notice it in our daily lives is that the effect is just too tiny. But trust me, it is always happening.
So you might be asking, Sir, why does all this matter? Well, it matters because this one central idea, that light is a wave, it connects everything together. It helps us understand things we've already learned. For example, remember Snell's law from ray optics? This explains why it works. It's not some magic rule, it's pure wave mechanics. And this idea is the foundation for everything we are going to learn next. Things like interference, which we just got a little taste of, diffraction, that bending of light we talked about, and polarization, how those special sunglasses work to cut the glare. It all starts here.
All right, Butcho, time for a quick summary for your notebooks. Please make sure you have these 5 points written down very clearly. They are extremely important for your exams. Ready? Point number 1. Light shows wave properties like interference, diffraction, and polarization. Point number 2. These things simply cannot be explained by ray optics. Point 3. You absolutely need coherent waves, remember, with a constant phase difference to see stable interference patterns. Point 4. The reason we don't see these effects easily in daily life is because the wavelength of light is incredibly tiny, just 400 to 700 nanometers. And finally, point number 5. Light is a transverse wave. Now, this last point is going to be super important when we study polarization later on, so keep it in mind.
And that brings us to a final and very fascinating question for you to think about. Look, it's one thing for me to stand here and say light is a wave, but how do we actually prove it in the lab? How can we build a model that not only explains all these new things like interference, but can also go back and derive the old laws of reflection and refraction right from the beginning? Well, the answer lies in a really beautiful idea called Huygens' principle. And that, my dear students, is exactly what we will explore in our next class. I'll see you